Where is he now?
Wait, is this mic for the online?
Yeah, so this one, you have to click on your...
My name is Maurice Hoogreef. I'm an assistant professor here and session chair today. And it's my pleasure to introduce the last speakers of this session here in this room. We have DSE Group 30, which is going to tell us all about a dual domain unmanned aerial underwater vehicle. Take it away.
Okay, welcome everyone, and thank you for coming to the symposium today. We are DSE Group 30, consisting of 10 aerospace bachelor students who have been working for the past 10 weeks on the design of an offshore, on the design of a dual-domain unmanned aerial underwater vehicle for offshore wind turbine inspections. In 2025, 25.2% of the total energy consumption in the European Union came from renewable energy sources. As the EU wants to increase this percentage to 42.5% by 2030, there's a big demand for new energy sources. Looking towards sustainable options, wind energy plays a massive role. Currently, there are 23 offshore wind farms under construction in the European Union only. As we get a lot of new wind turbines and they operate in very harsh environments, they require a lot of maintenance. Therefore, early damage detection, like detecting structural cracks before failure, is critical. We already have two ways to inspect these wind turbines. This can namely be done by manual inspection, which can be seen on the left, but this can also be very dangerous. Another option is using drones for the air and ROVs, which can be seen on the right, for the underwater inspection part. But as we requires two separate vehicles, this will also be very expensive. So what would happen if we could combine the aerial and the underwater inspection into one vehicle?
Allow us to present the aerial underwater drone for inspection of wind turbines. Apologies. Also known as Audit. Now let me run through some general specs. Audit has a length of 1.8 meters, a width of 1.1 meters, and a height of roughly 44 centimeters. It has a mass of roughly 24 kilograms, an inspection speed of 1.1 meters, allowing us to inspect a wind turbine in 62.5 minutes. Considering future cases where we want to expand our operations, we have included a maximum sortie time of 2 hours. While the later slides will talk about other subsystems in general, I want to just talk about some key specs of our drone that makes us stand apart from existing ROVs and underwater drones. The first is the fuselage. As we are expected to operate in depths of up to 60 meters, our fuselage must be able to protect the sensors and equipment inside. With a mass of roughly 4 kilograms, a length of 77.5 centimeters, and a radius of 10 centimeters with a skin thickness of 2 millimeters. Our drone has an ultimate depth rating of 100 meters. With most of the mass being built out of aluminum 5083, which is a highly corrosion-resistant aluminum. The front is also made out of borosilicate glass, allowing for clear imaging and sensing. Another key aspect of our design are the arms. Now, this is the most interesting in my opinion, partially because I'm the one that helped design it, but also because it serves a very key role. In order for our drone to fly efficiently, the propellers must be extremely large. But in order for the propellers to not hit the drone itself, we must place them quite far out. This means that a longer arm leads to more surface area, which means more drag. To minimize this, we have developed a telescoping system, courtesy of Aerospace, with a mass of 1.1 kilograms, a telescope length of 80 centimeters, and a fully collapsed length of 45. The material is also made out of carbon fiber reinforced polymer. Now, let me explain how this works. First, we have two segments, as shown on the screen. The blue, which is the propeller arm, and the orange, which is the fuselage arm, as they are connected to the propeller and fuselage, respectively. Then, the fuselage arm is hollow on the inside, which allows the propeller arm to slide in and out freely. The way it works is quite simple, actually. First, we have a spring. The spring wants to push the propeller arm outwards. Then we have a cable that has two purposes. First, it ensures that it stays at a maximum extended position and also allows us to pull it back in when required. Another key feature of our arms are what we call the go posts. These go posts serve a very extremely important purpose. As it turns out, our propeller blades are not fully connected to the propeller itself, allowing them to flap around if not rotated. As shown on the left, when the propellers are rotating, they are straight out, but when they're not, they could be flapping around, causing potential damage or unwanted drag. Thus, we invented the go post system, which allows them to fold neatly in, as shown on the right. Going more into detail about the specific propulsion units, for the aerial phase, we use the Hobbywing X6, which is roughly 800 grams in mass, has a tip-to-tip diameter of 60 centimeters, hence the need for the telescoping mechanism, and are able to produce roughly 116 newtons of thrust in aerial phases, as well as being able to operate from negative 20 degrees Celsius to 50 degrees Celsius. For the underwater phase, we use what we call the Blue Robotics T200s, which has a mass of roughly 430 grams, a diameter of 7.6 centimeters, and are able to produce 66 newtons of thrust each, and operate in temperatures between 2 and 27 degrees Celsius.
Now that we've taken a look at the general system, let's take a look at how we do our actual mission. Of course, to be able to inspect our wind turbine, we need to be able to see. For this, we opted to use three different types of cameras. First, a hyperspectral camera. Second, a conventional RGB camera. And last, an event camera. Let's go over all these cameras, starting with the hyperspectral. A hyperspectral camera, in contrast to a standard RGB camera, inspects using a full range spectrum instead of just red, green, and blue for a conventional camera. For our camera, we have a spectrum range from 400 nanometers to 1000 nanometers with 281 bands, allowing a spectral resolution of close to 2.1 nanometers. The output of a hyperspectral camera can be interpreted as a 3D data cube with two spatial dimensions and one spectral dimensions, as shown on the left here. This picture shows a hyperspectral image of a plant, which also shows that we are able to decompose the picture into all its different wavelength components. Due to this property of a hyperspectral camera, it's very good for seeing the chemistry of a structure. For example, for seeing corrosion or small material changes in a structure. However, due to the way water absorbs light underwater, we also opted to use a standard RGB camera. For our camera, for the RGB camera, is used mainly to inspect bigger tracks, such as shown on the left here, on the wind turbine. Our camera has a resolution of 4K at 60 FPS and is optimized for low illumination, which is good when inspecting underwater or possibly in the dark. For our inspection model, we use a YOLA model, standing for You Only Look Once, to determine whether something we're looking at is a crack and give a confidence score. Next, we go to the event camera. In contrast to normal cameras and a hyperspectral camera, which take light, a hyperspectral camera only looks at the brightness of a pixel and not necessarily the wavelengths, illustrated by a picture on the left. Using this camera, we can detect small cracks when flying around using a specialized algorithm running on our onboard computer, which I'll get to later. However, due to the fact that the event camera only detects changes in light, it allows for a very high refresh rate and is thus also very good for object avoidance, especially in the air. Connected to the event camera is a neural processor, which is used to immediately process data of the event camera and which is sent to the onboard computer, as well as save power by only being used when big changes are detected in the output. Next, to inspect, we need, of course, to be able to see. For this, we opted to use two lights, each shining at over 1500 lumens for a mere 15 watts, allowing us to be able to operate in deep waters or during the night. Furthermore, the lights are fully dimmable, allowing for proper control of the lights without washing out colors, as seen here on the left. The most left shows the picture of the lights turned off, while the rightmost picture shows all the lights fully turned on, from which it is obvious that the colors are washed out and it's not clear to be able to see what it is. Especially for the hyperspectral camera, it's very important to be able to see all the reflecting waves from the object we're inspecting. Next, for the onboard, we'll go to the onboard computer. This processor is used for processing all the data and makes use of an edge AI architecture. This processor takes the data from all the cameras, namely the event, hyperspectral, and the RGB camera, and turns this into a likelihood score of if what we're looking at is a crack or not. Furthermore, we have an onboard data storage of around 4 terabytes NVMe drive, allowing for very high reading and writing speeds for quick processing, as well as plenty of storage for the over 200 gigabytes of data generated for each mission. But now that we look what we use to inspect, how do we actually inspect the wind turbine that we want to see? For this, the drone starts in a lawnmower pattern, meaning the drone goes up and down in straight lines around the wind turbine, similar pattern as someone would mow their lawn. As mentioned before, the drone has an inspection speed of around 1.1 meters per second, which was determined based on the maximum allowed pixel blur from our requirements, as well as the specs of the camera that we are using. The drone starts off by inspecting the aerial part of the monopile, by inspecting the blades, as well as the pile itself, before transitioning underwater and inspecting that section. The transition will be explained more later. Lastly, we looked at power. Our requirements stated a clear maximum capacity of 5 kilowatt hours for our battery. For this, we had to do a detailed power analysis of our systems, including the propulsion, the sensors, as well as all other systems on board, such as the navigation and the communication. Based on Monte Carlo simulations, which we ran over 10,000 iterations, simulating environmental conditions such as wind speeds and current speeds, it was determined that the 5 kilowatt hours was enough to meet more than 99% of all missions that we plan to do. However, using its conventional lithium-ion batteries, the weight of the battery would be in the order of 14 to 15 kilograms, which would be way too high for our mission. And thus, we opted to use a new type of technology called solid-state batteries. Compared to lithium-ion batteries which have energy densities in the order of 300 watt-hour per kilograms for state-of-the-art, solid-state batteries have been proven to have energy densities of up to 700 to 900 watt-hour per kilograms. With big companies such as Toyota having already published roadmaps to commercial production by the end of 2027, we believe that this type of battery is a very good fit for our system, which allows us to meet our mission and our requirements.
Now onto stability and control. Our drone needs to be able to operate in water and air in a very harsh offshore climate with high wind gusts, waves and currents. One of the requirements was that it should be able to operate in a Beaufort sea state of 4, meaning wind speeds up to 50 meters per second and 2 meters high waves. These can even be made worse by the wind turbine itself. To be able to do the whole inspection fully autonomously, we started by estimating some aerodynamic parameters like the drag coefficient using computational fluid dynamic simulations. We then use these parameters in our motion model that estimates the behavior of their drone. This motion model was based on 2 state vectors, one 16-state vector in the aerial phase and one 20-state vector in the underwater phase. These state vectors are based upon the speed and on the sensors like the depth sensor, but also how fast the angular momentum of the motor is. These states are then communicated to the controller, which consists of several layers. One is the predetermined flight path around the wind turbine for inspection using a lot of waypoints. Then we have an outer loop that controls the position and an inner loop that controls the attitude of our drone. Furthermore, we have the event camera, like Odin mentioned, a LiDAR and sonar for underwater to detect obstacles. When an obstacle is detected, an artificial potential field is created around the drone, which deflects the drone away from the obstacle, after which it will return safely to its flight path. Then the most important part from our mission is transition. The audit has 4 different controllers, one for in the air, one for underwater, and it has 2 separate controllers to be able to do the transition, one from water to air and one for air to water. These motors control specifically when the arms retract when it goes into the water and when the arms fold out again and start up the motors on the right moment. It's able to do this by 4 water sensing sensors that are placed in the aerial propellers itself. It should also be able to do this in quite a rough environment and the Beaufort sea state. It's able to do this because it's lightly positively buoyant, meaning it will float up to the surface, and due to the placement of the underwater thrusters, which can also help in the motion upwards. Now onto sustainability. Sustainability was a vital part in our design process. More than 80% of audit is fully recyclable. We use onboard power-optimized edge AI without using any cloud services. We use cutting-edge solid-state batteries, which have can handle more charge and discharge cycle than conventional batteries, extending the lifetime of our drone. And at the end of the lifetime of solid-state batteries, they can be way more recycled than conventional lithium-ion batteries. But most importantly, it can have a great contribution to the green energy sector as a whole. Not only cutting down emissions during inspections, but also extending lifetimes of the wind turbines. Audit greatly reduces cost and time needed for inspections. Wind turbine operators can thus perform way more inspections, catching cracks and other defects way earlier on. If then maintenance is performed, the lifetime of wind turbines on sea can be greatly extended.
So far we mostly looked at the technical details of our design, but of course the financial aspect cannot be ignored. What we see over here is a breakdown of our subsystem cost, which has been determined using raw material estimates and supplier pricings. It can be found that the inspection, navigation and communications are quite expensive subsystems, which can be explained by the fact that they have very expensive hardware. For example, the hyperspectral camera, which costs over 11,000 euros. Adding all of these costs together gives us a total cost, including a 10% margin, of almost 45,000 euros, which fits within the required maximum prototype manufacturing cost of 50,000 euros. The financial team aims to return the investments of the prototype within the lifetime of the first drone. The lifetime has been determined to be approximately 1 year, and the drone has to perform 1,000 missions. As we assume that it can perform approximately 10 inspections per day, this would mean that audit will be operational for 100 days a year. The operational cost is mainly dominated by the support vessel and its fuel, and adding up to over 6.5 million euros per year. As this assumes that we use the support vessel only for one drone and not for taking multiple drones, or for example by taking equipment for inspecting the inside of the wind turbine, the operational cost could go down by approximately 5 million euros when upscaling our project. If we look at the development cost, as all of it is not completely developed yet, unfortunately, we used our production plan and the average gross engineering salary in the Netherlands, which is 41 euros per hour, to determine our development cost to be just over 1 million euros. As audit operates in very harsh marine environments, it also has a very high maintenance cost. The maintenance cost will be approximately 35% of the initial hardware price, adding up to 15,000 euros, and therefore when summing all of our costs together, the yearly cost will be 7.6 million euros. If we aim to return these investments within the first year of our prototype, this would mean that we have to charge 8,000 euros per turbine, leading to a final profit of 382,000 euros.
Finally, I want to highlight some of Audit's capabilities. Audit is a beautiful solution to combine the underwater and aerial part of wind turbine inspection only into one mission. It can do this in almost 1 hour and will greatly reduce cost. Our prototype is 45,000 euros, but when we ramp up production, this can be even brought way down. It can do this in the most roughest of conditions in the offshore environment with high wind speeds, but mostly I want to emphasize Audit can make a great contribution to the green energy sector as a whole. Thank you for your attention. Now I would like to invite my team up to answer some questions.
Thank you very much, Team 30. We have about 20 minutes for questions, so feel free. Yes.
Yes, thank you for a very nice presentation, video, and all that stuff. Very well done. So you mentioned that combining the aerial and the underwater features were being done because of cost, and that you're having one vehicle rather than multiple would be more cost efficient. Have you looked at the costs comparatively for individual, like an aerial plus an underwater vehicle, to compare the cost? Because I guess you've got to make some compromise. You've got to have, I mean, you're bringing what would normally be in the air underwater, so you've got to design that maybe a little bit differently. Maybe it has to be a little bit more expensive. So let me talk a little bit about that, the comparative cost to doing these separately.
Can I hold this? Yeah. All right, so we indeed looked into it. We started off our research by doing a market analysis in the first place. So looking into the options of, or like the current market of wind turbine inspection methods. However, the prices are not readily found on the internet. We try to request some costs to make an estimation. So with that, we found that the separate operations for aerial would be way cheaper than our drone right now. However, ROVs are more, the current ROVs on the market are more, have more capabilities than our drone has, because they don't have to account for any weight limitations. They don't have to fly at the same time as our drone has to. So those operations are actually more expensive than our drone right now, but it's also have more capabilities and can do more specific investigation and inspection of the underwater turbine. So our estimate is that we actually are a more cheap option. However, it should be noted that our benefits lie mostly in the logistical preference of the combined inspection not that we provide more quality or deeper, because we had to, we were limited by combining those domains.
Thanks guys for this interesting presentation and James Bond introduction. Last bit. Offshore wind turbines are a very known accumulator for floating stuff like fishing lines, like fishing nets, like seaweed, algae, and you want to transition that surface with 12 propellers. How do you deal with that?
Right. I think Ravi. Okay.
All right. So just to like this. All right. So just to repeat the question, I think you brought concern about obstacles in the water that we have to deal with when we do the transition, right? All right. So first of all, there is an obstacle avoidance system that we use called stop and hold underwater. So there are 2 radars pointed up and down, and a 360 camera that can see 360 degrees around the whole vehicle. So the idea is that if an obstacle is detected within these sonars, the vehicle stops and waits for the obstacle to clear before going ahead with the transition. We can't do full obstacle avoidance underwater because sonars are very expensive. So to get 3D full coverage around a underwater vehicle, that would cost upwards of 30,000 euros. And that doesn't fit within our budget. That's why we resorted to using a stop and hold model. But if I could show you a diagram, does this work? Go to this part here. We have a full state machine which shows you what should and should not be done at every phase of our landing or takeoff. So for example, if you go from landing phase A, landing phase 2, it says switch to set state correction from 4 FMCW sensors. So at different phases of the landing, we have different sensors that are being used to make sure that the propellers don't hit obstacles on the way down and on the way up. And this framework is running at 400 Hertz. So it makes sure that every phase we have a solution if an obstacle is detected. Does that answer your question?
Thank you.
All right.
I saw a question over here.
Yeah. Maybe following question of my colleague also, wondering if this hybrid solution, although very inventive, would indeed also be the most efficient solution, because indeed having to carry much more load up and doing inspection above water and then underwater. If you have looked or considered an option to drop your underwater unit and then do them in parallel, and also would that help? Because then, for half the time you don't need to carry your loads. I think also it can contribute to your the time.
Yes, thank you for your question. And to repeat it, the question is whether we have looked at the option of separating the two while doing it simultaneously, and if that would be better. For our system, that is something we considered in the initial design phase. But at some point we determined that, first of all, it would be heavier as one integrated system, as well as that the navigation and communication would be much harder, as it would likely have to be tethered for communication to either the drone or the ship, which would make it pretty much impossible to do simultaneously. Because currently as well, the conventional method for ROVs is to use tethered connections, which is something we did not opt for. However, the systems that we use for our communications are also very expensive and thus did not fit in our cost budget as well. So pretty much to summarize, we have considered it, however we determined it was outside our cost budget, mass budget, as well as that it would not allow for simultaneous operations, if that answers your question.
Yeah, that's things.
Plenty of time for more questions.
Plenty more questions available.
So you're propelling things underwater and you're propelling things in the air, right? So
Did you look at or consider just using the same propellers for underwater and in the air? And what were your conclusions?
I'm just going to hold this. Yes, we spent quite a significant amount of time looking at combining the two, as well as some preliminary designs. The short answer is no, it ruins your efficiency completely in both domains. The reason being that underwater propellers, I don't know if we have a picture, but if you've ever seen a boat propeller, the angle of attack is extremely different, and the aspect ratio and the shape of the propellers as to an aerial drone. So this kind of drone has actually been done in the past by university students. There are some videos online, and what you can see is they operate quite well in one domain, but when they switch domains, they're extremely slow to react, and overall unfeasible for this kind of mission. I hope that answers.
As a structural engineer, it will be, it's great to know, hey, there's a defect, but our next question would be, what is the location of the defect? Would you be able to tell that as well? And how?
Here we go.
Thank you for your question. Yes, we can. So first off, we have an array of sensors and communication devices that allow us to know our position with a certain degree of uncertainty, of course, due to the marine and underwater aerial part of the mission. But most importantly, our data recorded by our cameras is timestamped, and the whole mission is timestamped as well. This is stored on an SSD of up to 8 terabytes, so we have no storage problems. And this is really simple. Then our AI infrastructure inside the drone processes this information, but as we mentioned, but also the data is stored, so the off-board or off-mission analysis is also possible.
And what is your zero reference for your location?
Our zero reference?
Yeah.
Well, so we use the cylindrical coordinates for the monopile, and also it's ship tethered, so the data relays from the ship to satellite on the drone as well.
Can I add something?
Yes, of course.
I realized that during our presentation we haven't explained what the word monopile means. Thank you. The type of turbine that we are analyzing is called a monopile turbine. Essentially what it is the most common type of turbine used in Europe and worldwide. It is a turbine that is very simply a cylinder from top to bottom. So the monotile refers to the underwater section, and the tower refers to the above water section. The monopile is generally a different material, and so that would be our 0 point of reference, as Miguel was saying, since we use cylindrical coordinates around that monopile. I hope that answers. Oh, yes, Ravi.
Also, I would like to point out that so we didn't explain this properly because we didn't have time, but the controller works with offline waypoints that are created before the inspection. So the whole trajectory is already on board the UAUV before it even takes off. So the timestamp, you just have to correlate that back to our offline trajectory, and then we know exactly where it was. And at the same time, all the states, so the states from here, the destined states are saved on board with timestamps. So at any given time, we can tell you exactly where the drone was located. So it's just about matching that to our crack detected, and then we know where it is. All right, hope that answers your question.
Good team answer.
Saw some more hands raised. Yes, please.
Yeah. And given you had a sort of maximum weight, given the budget, what is the next instrument you would have liked to add to the machine had you had more weight or more money?
So we talked about the fact that we couldn't do 100% obstacle avoidance because of the limitation in the underwater sensors. I think that's been a big point of contention that we've worked on a lot to try and get as much possible coverage. And so actually it's on the next slide, there we go. So you can see that in the aerial domain we are completely flooded with sensors, we have everything we need, but underwater we're quite limited and we only have 28% spatial coverage. So I think given more freedom in mass and even cost as well, we would have liked to have more sensors that could help in that aspect.
And if I may follow up,
Yes.
as a wind farm operator, what do you think your client would have most wanted to also know that he now can't know because you only have the 3 cameras?
That is an interesting question. I would say the thing that the wind turbine operator would probably want to know is, well, can I give this actually to Odin? I think I'm underqualified for this.
Yes, sorry, so to repeat your question, whether we have something that the wind turbine operator would prefer over something that we don't have now. I think in that case, that's where commercial ROVs come in, where because they don't have to care about weight or volume or whatever, they are able to, for example, use manipulator arms. For example, if there's algae growing on the bottom of the monopile, or whether there's some other, I don't know, rocks around the bottom or something. This is something that we don't have, as simply we don't have the mass and space budget for that. But I feel like that's something that, sorry, to go on to that. Currently, the way we plan to do it is, for example, say we run into something covering the wind turbine, we just send a signal to the operator that's like, hey, this is something you might have to look at in more detail, because we can't look at that, if that answers the question.
What he said.
Odin, I could add something.
Do you want to add?
Yeah. Current ROVs, they have something called, like, they use audio and sonar to find cracks. So they actually touch the object with the sensor and then send audio to do it, and they can get better resolution, like information on the cracks. So I guess we would also add audio sensors. So, but that would require touch the actual structure.
Yeah, that's what I would do as well.
So a couple more hands raised. First in the front, and then we go down.
Back to the structure of design, which was presented in the beginning. So I saw you have 4 separate carbon beams, armed, telescopic. First question, why 4 and not 2? And also on the telescopic system, it's nice how it extends and contracts. How did you counter for the rotational issue in your telescope? And have you considered other solutions
Just to repeat the question, I believe the first question is why the arms were not in 2 beams. If I can go back to the slide where we show the drone from above, you would see that right now it's kind of off-centered because we want to push this outer, the propeller arm back in quite a lot. But if we were to put it in line, then these two, when they extend back in, they would bump into each other. So that's why we have to put them out of plane. Your second question, I believe, was
rotation issue?
Yes, the rotation issue. While it's not clearly shown in these images because we didn't really want to show from the bottom, the shape isn't a perfect circle, but rather a semicircle with like a notch into it. So that provides something like a guide rail for the entire system itself. And did you have a third question?
No.
Okay, sorry.
Custom carbon beam, but doable.
Yeah,
right?
It's a bit more complex, but I believe this is the most efficient way of doing it. So.
Okay, thanks.
Yeah.
And maybe the final question all the way in the back.
Yes, thank you. I was wondering about charging. Will there be a sort of charging station on the wind farm, or will you charge it on the boat? And if it's charged on the boat, is there a way to charge it using green energy if it's on the boat?
Can I do that? Can I hold it?
Yeah, okay. So to repeat your question is... So to repeat the question, is there a charging station and do we use green energy? So we, in the design, we were thinking of 2 different solutions. One is a charging pod on the wind turbine, and one is charging on the vessel itself, the ship itself. Now, for the complexity of our design, we have chosen to go with the vessel, as the charging pod on the wind turbine station itself is too unreliable at this stage. This, however, is still a way we want to go in the future with this project, if we were to develop this. Now, as the vessel is more reliable, for charging the drone, we can still use green energy. However, the vessels mostly do not use green energy. So the charging of the drone itself is minor energy consumption with green energy, but the vessels still do not use green energy. You can answer.
Thank you. Also, because we use a solid-state battery, this type of battery you can charge super quick in 10 minutes or less. Might we have an image for this? Oh, yeah. And also, it's important to mention that our design includes all of the sensor arrays and the inside systems in a sort of, how you call it, like a plater. It's not a plater, okay? But you can pull it out of the drone, so it's easy modifiable. And in that sense, you could even get more batteries with your vessel, so that you don't need to charge on the vessel itself, but you can charge them before the mission and afterwards, using green energy sources if you'd like. That'd be nice. And that way we solve this issue. Yeah.
Right, thank you. Oh, one final burning question, if you keep it short. I keep the answer short.
Just the scan that you are doing, so you have some findings, and how do you determine the findings in terms of criticality and priority? You can have more than one finding.
Yes, so your question was how severe would a crack be if you were able to detect it, right? So our AI model uses 3 different things, like Odin said, for an RGB, the hyperspectral, and the event camera. So what an event camera is good at is looking at vibrational cracks. And the hyperspectral can look at chemistry between materials, and RGB can see the cracks itself, and that gets combined into a sort of final score, and this is given to the crack at certain locations, like the question before, and that determines how severe a crack is. If that answers your question. Thank you. And I think thank you all for listening, and for the people home listening, and yeah, have a nice day.
Before we go to the final stage of this event, some administrative announcements. This was the last presentation here in this room. There are some more presentations in 2 other rooms, so if you're interested, feel free to attend. We'll have the reception starting at 4:45 with refreshments near the main entrance. Then at around 5:30 we hope to do the award ceremony. Now, the last information I got was that we'll be outside with a live stream to the big lecture hall, so that if you feel uncomfortable outside because of the temperature, you can sit in the air-conditioned room, and that is lecture hall A. Then for the jury members, if this was the last presentation you were attending, don't forget to pass on your scoring card to me before you leave. And then I would like to ask the tutor to come over and hand out diplomas, because for 8 of you today is also the congratulations to all of you, especially group designers.
Kijk.
And if you want to take pictures, come forward.
Okay. Once again, congratulations for not only your design and how you collaborate with each other in this for this project. I was very impressed with your design. I should really confess. So But now it's time for your graduations, and I'm honored to give you these diplomas. The first one. Sorry if I pronounce it wrong. Philip Hendrik Gonçalves Silverinha. Second one. Fredrike Elizabeth Gransbergen. Brui Mann. Miguel Obina Sanchez. Noah van den Odenhoven. Andrew George Price. Ravindu Kalinga Bandara. Odin Gerard Carr Tyson. Can I also join that?
Wait, with the design? Group picture, everyone? Group picture? Guys, let's do group picture.
Group picture?
Can we don't